Today's topic is a neural net, and I think many of you, some of you, have taken some kind of a machine learning subject, or neural net by training or whatever. And so the materials I cover today is not really going too far from the just a standard machine learning class. So if you already knows that, please bear with me. This is just a review for you. But I learned that many of you have never really studied this officially, so it may be a good opportunity for you to learn. Yeah, neural nets definitely useful, and it is one of the major techniques in the nonlinear system modeling and the machine learning. Looking at the history of neural nets, it's basically going up and down, up and down. This is maybe the third wave. So I just plotted based on my very much subjective judgment, some kind of impact and then social interest, against the time since 1940. So we saw, at least 3 waves over here, and then in the early stage in 1940 to 55 or 60s, there's a first wave came in. Basically, came from neuroscience study, and then people tried to put together the mathematical model, that neural model, starting with the McCulloch and Pitts, 1943, and Frank Rosenblatt developed the so-called perceptron for some simple, pattern classification, 1958, and Widerhoff stochastic gradient descent method is one milestone at that time. Then and went to some quiet time, and our colleague, Professor Marvin Minsky, he just argued that the neural net is not the right way of handling the the artificial intelligence, and actually pointed out in some counterexample of the the things that cannot be handled by perceptron, the other techniques, and the first wave. And after that, this was a really killer. It went through some quiet time, but since the mid 70s and then 80s, it came back again with the multi-layer neural networks, and with the error backpropagation algorithms developed independently by Rammelhout, McClelland. But I know more importantly, the original idea came from Werber's 1975, and then and many other techniques, including reinforcement learning, Sutton 1984. This is basically an optimal control in the neural net version, and then that actually showed kind of a good interest sometime. And then going through some quiet time, and followed by some disappointment. The one time when people just solved every problem by multi-layer neural net with the error backprop, no, it's not quite right. And then, it's gone through some quiet time. And since the late 90s or 2000, it came back again. And with the new techniques, deep learning. And that the convolutional neural net, CNN, by Fukushima, 1980, and then recurrent neural nets, NMR to Jordan, and the long short-term memory, perhaps this, being used for voice recognition. And then the hardware side, the GPU is actually quite effective to handle the neural net computation. And then indeed, we saw a lot of successful, not a lot, but specific areas and quite successful in particular, voice recognition and image processing are two areas which are really, really actually useful these days. So this is a quick history. Now, what I'd like to do today is basically focusing on some of the basic things, and artificial neural network, basic neural model, gradient descent, nonlinear classification, exclusive OR problem. This is one kind of counterexample. And then going to a multi-layer neural net, birth of error backpropagation algorithms, and some of the properties and the kind of tips for training the neural nets will be discussed at the end. Okay. So starting with the neural model, a human brain has approximately 14 billion neurons, so we must be very smart. Although this one is a small fraction compared to the number of cells that we have in the body, that's actually many trillion cells. But these neuron cells are acting in a very special way, and it is basically massively parallel and distributed processing, very different from the traditional tuning of machine-based computing. So people really look at this, and from a certain point, people really look at the mathematical description about the function of the individual neurons, and then that's one of them is Donald Hebb's 1949. He proposed the so-called the Hebbian rule, and then when the synapse connecting the some input x1 to output y, for instance, that synapse is actually increased, weight is increased, and when the output y is persistently firing in response to input, for instance, x1, if that happens, then the synapse weight w1 is increased. So this is very simple rule, but I know in fact that this is a kind of laid out in the basics, foundations of the neural net learning, and plasticity of the brain is explained at the very simplest level, like this. It turns out that this guy, it's both input and then output must be fired, then the W1 is reinforced. This particular structure is very, very similar to Kalman filter and then recursive least squares, as we discussed later. So artificial neural model, so it has a bunch of input coming into through a synapse to this neural unit. So we first take the weighted sum of the inputs. Z is the sum, and then Wi is the weight multiplied to the input and xi. And then the resultant sum Z is going through some output function, which is typically a nonlinear function. And then y hat is actually g of z, and then we describe the nonlinear function, output function by g of z. Okay. And then this one is compared to the correct one, and then that's actually supervised learning mode. And supervised learning, that we deal with the two types of problem. One is a regression, continuous output, versus classification, discrete output, yes, no, class 1, class 2 type of classification. So now, when we actually present input output the training data to the neuron, output is compared to the teacher signal, and error is fed back to change the weights, and we can apply the prediction error method. Formulation can be done based on the prediction error method. So that's actually one of the big framework we've been using for many of the materials that we discussed so far, right? So let's look at this. The neural net training based on the gradient descent. So to begin with, I'd like to show some of the important theoretical results. So we look at a very simple case. Output, the summation is taken, Wi xi, I equal 1 to n, as before. But an output function, let's consider some linear function. So if the linear function are like this, this z is basically the output. So assuming the slope is 1, and this is output, right? So what we'd like to do is to find weights using the training data. This is the training data, so that the squared error may be minimum. So this is the error, squared error, or in machine learning literature, often people call this a cost function. This cost function is basically depending on the weight W1 to Wn. So what we like to do is first look at the gradient of this cost function with respect to weights you want to modify, say W. And then, in some way we compute this in a gradient and move the value of W in the opposite direction to this gradient. So that's a gradient descent method, right? So the delta W, that weight we like to change, is proportional to the gradient of this cost function, the Jn, with respect to Wi, and then we multiply learning rate, rho, and then actually this one, the gradient descent, so we have to put the minus sign over here. Learning rate is something that we discussed. This must be tuned carefully. So now let's compute this in a partial Jn or partial Wi, and the Jn inside of it, Wi is involved through this predicted value y hat. So yeah, we presented many data, and then each of them provide some output and compared to the correct one, and then we create some errors, and then error squared is actually taken here, right? So differentiated with respect to Wi, first we differentiated this one, and then differentiated in y with respect to W, so expanded this way, right? 2 comes out, here. Okay, now we assume a linear output function to begin with. So, this part, the Wi, xi, and then differentiate it with the Wi, leaving only xi, and for the jth, data points. And here the, prediction error, right? So this is exactly the way to change is to be proportional to prediction error times, where are we? Yeah. So sorry, I pushed in the wrong direction. Sorry. So a prediction error times the input. So what comes into your mind? Maybe input may be extended to regressor, right? Regressor times prediction error. So that's actually exactly the form we saw in the recursive least squares and the Kalman filter too, right? Recursive least squares. This is actually the regressor, and we multiplied by some special gains. And the Kalman filter, that gain is more sophisticated, right? So basically, this is the common structure we see in these algorithms. Okay, now looking at this method, gradient descent method, it's called the global gradient descent, and in the following sense. So weight change delta Wi is to be made after you present all the samples, j equal 1 to n, and then you evaluate this, then you make one change to the weight, right? So until you present all the training data, you cannot make any correction to the weight, right? So, the size of the training data increases, and sometimes going to many thousands and so forth. A large memory space is required to store the results. Well, the memory is not so much issued these days, but simplicity in the computation is more important. But memory size was a very critical issue back in the when Frank Rosenblatt developed the first perceptron. So anyhow, they tried to change this rule. They tried to change this, modify this gradient descent method. An alternative method is called the delta method. And shown here is the delta method. So, we just introduced yet another index here, K. K is to indicate the case presentation of training data. Okay, so as soon as you present case samples taken from your case example from the training data, you compute this weight change and execute that weight change immediately. Where we use a delta K. Delta K is actually correct the signal output minus predicted one, so that is given by W and K, right? And the case for the case presentation. So once we do this, of course, sometimes depending on which particular samples you present, the gradient going sometimes going this and sometimes going that. But imagine that we present this repeatedly. If we have a total capital N data points in your training data set, we present this one by one, and then for each presentation, we make this change, right? And then this one set of presentation capital N is called the one epoch. And then we repeat this presentation many, many times. So the previously, batch processing is to present all these and store all the results and then determine the gradient as an average of these results and make one change over here, right? Instead, we make a quick change to each presentation and repeat it many, many times. So maybe the trajectory is actually zigzag, but stochastically this is to converge to a certain value. So that is the idea. So N training data are randomly presented to the neural net and then make weight change N times. Repeat this sequence of N presentation, it's called an epoch, and then many, many times until it converges. So compared to the full gradient descent method, we call that the batch processing. The Wiedehoff algorithms may be erratic in each step of weight corrections, as I said, the zigzag, right? Since it evaluates the gradient based on only one data point, one example from the training data, but no need to store, on each presentation result, they're much quicker in making corrections, right? Particularly for a large training data set. This is something preferred architecture for the neural net community. It is actually massively parallel and then distributed processing. That's what they want to pursue. And that really makes sense. But the question is, does it converge? Where to converge? In fact, there's a lot of papers on this issue, and I'm just posting one, very primitive, original mathematical communities, mathematics communities, the paper back 1951, Robbins and Monroe's. And here, for linear output functions, convergence conditions have been obtained under the following three conditions. So first of all, this is the learning rate. This is the number of iterations presentation. If you use a constant learning rate, it does not converge. Learning rate must be varied and basically starting with the large one and actually, getting smaller and smaller. What is the speed of, reducing this learning rate is a question. And all the way to converge to their optimal values with probability 1 when the following conditions are met. Okay. So first of all, at the end of the day, as you increase the presentation number K in going to infinity, it must be 0. At the end of the day, it goes to 0. Okay. But if you take the sum of these values, meaning that the area beneath this curve, that area must be infinite. This is to prevent the case, and when actually this goes down too quickly, too quickly, there's no chance for weights to converge to the right one. So this condition prevents all the weights from converging so fast that the error will remain forever uncorrected. So, that is to prevent this kind of stuff. At the same time, this shouldn't be too slow. So if you take the squared of that, the squared must be bounded. Squared sum of this, learning rate must be bounded. But ripping off the square, that's an area itself must go to infinity. So this guy is to ensure that the random fluctuation towards the end of the training are eventually suppressed. So how we can actually pick the law? And then one well-known learning rate is to use this function, something constant divided by the number of presentation k. This one basically goes down in this way, and then that meet all three conditions. The k infinite, this goes to 0, right? And if you take the area that is infinite, and then k square, 1 over k square goes to bounded value. So this is a very special case. The simple and the output, result is very clean. Of course, the later many important works published, and they are much more getting closer to reality. But the conditions are quite complex, so we do not go into that more than this. But I know this particular theory, stochastic gradient descent, laid the some foundations of the neural nets and that we see today. Okay, now let's go into a little bit actually, in the next phase. So this is second wave of multi-layer neural nets. Before multi-layer neural nets invented, and then error backpropagation algorithms was invented, there was some kind of a struggle time. And first the Rosenblatt perceptron, it has a quite a significant limitation to it, and the committee basically overcome on that problem. So that comes from the linear separability conditions. So shown here, the two inputs x1, x2, you can treat it as features of some patterns to classify, and if x1, x2 combinations actually right lower side, and then a red group is actually top on the left hand side. We can actually classify these two sets by drawing the straight line like this. This is called linearly separable in a program. But if these two are mixed up in this way, there's no straight line to discriminate, classify these two. It's called not linearly separable in a program. And it's hard and a little bit harder to do, right? Now, one simple example that basically addressed by Professor Marvin Minsky, and he denounced that the kind of things that you've been doing doesn't make sense. It can't actually solve such a simple problem like exclusive OR program. Now let's look at this. Exclusive OR, perhaps you know that in electric engineering logic, input, if two inputs are both 0, 0, output should be 0. And one of them is 1, the output is 1. And if both inputs are 1, high, then actually output is low or false, right? So this is something, a simple example for pattern classification. So if I plot x1, x2 in here, so just one of them is 1 or true. So these two middle cases actually plots to these 2 points, and both are 0 or both are 1. Basically here, right? So what we'd like to do is to classify this group class 1 from class 0 over here. Now let's think about some neural net, neuron, single neuron. So, input the x1 comes from this input, and then the x2 comes from here, this column. And also we include some constant input bias. And we assign the weights W1, W2, and W3 over here. So Z is actually, X1, W1, W2, X2, and then W3, right? So this is the, sum of the weighted sum. Now, let's think about the sum output function to be almost a binary, 0, 1, or, for the purpose of training, we like to have something smooth and functioned like this. So 0 and 1 are, are connected through some smooth, transitions like this. But then the point is that if Z is basically, 0, then it is classified to output 0, class 0. And then, Z is actually positive side, it is actually 1. Okay, so let's actually use this kind of function for classification. It's called a discriminant function. So if G is equal 1, Z equal positive, otherwise actually 0, right? So this represents the one straight line. The threshold is basically, let's say that Z is set to be 0. Then we have this equation. And then this one is to show the one straight line in the x1, x2 plane, such as this, right? But no matter how you pick the weights W1, W2, W3, you cannot actually, separate these two classes, right? No matter how you draw the straight line, you can't actually classify this. So this problem is not the, the neural net like this cannot handle the classification problem. So, however, here's a kind of interesting point. Let's actually consider a nonlinear discriminant function, Z equal the function of x1, x2, x1 plus x2 minus 2 times product of x1, x2 minus, bias minus 1/3. Okay, let's actually plug in, x1, x2 from the truth table of the exclusive OR. If both are 0, 0, 0, 0, this is 0 minus 1/3, right? And both are 1, 1, the 1, 1 minus 2, 0, and then again in a minus 1/3. So classified to 0, negative value, right? If only one side is 1, the other is 0, this one 0. So 1 comes out to here, 1 minus 1/3, 2/3, which is actually, positive. So classified to 1, right? In other words, actually, these two, classes are classified in this way. So this one is kind of, this represented some of the, parabolic, hyperbolic, functions and like this. Now, more interestingly, let's replace this term x1 times x2 by a new variable, x3. So if you have x1, x2, and additional x3 axis sitting here, then actually, 4 points, 0, 0, 1, 1, and then actually 1, 0, 1, 0, 1 can be plotted here, right? So this particular point, because we add x3, both x1, x2 are 1, and x3 is 1, so take this particular the point, apex here. So interestingly, these 2 points basically belong into class 0. And then these 2 points here, I can't see it here, but another point over here, classified to class 1. And then these two classes can be separated by this plane in the 3-dimensional space. So in a sense, by adding this variable, new variable x3 equal x1 times x2, the problem is recast to be a linearly separable problem, right? Now, interesting point is that this is possible by creating x3. So now the idea is that if you add the one more unit over here, neuron unit over here, we can create something similar to the role of x3 over here. And then x3, x1, x2 coming directly from this input. If you just add one more axis and then try to train the weights involved in this, you can actually solve this. It's just a standard method because it is linearly separable. So let's look at this guy. Okay, so this one is to take x1 with the weight plus 1, and then a constant 1 with the weight minus 1.25. And here, maybe you can say that, in this guy. And then it's still with the weight plus 1. So in case of 0, 0, this is going to directly here, 0, 0, 0, 0. This minus 1.25 remains. So this one is basically negative. So the output is 0. So, nothing happens over here. So only this guy remains minus 1/3. So this one is class 0, right? Now, both are 1, 1, x1, x2, both are 1. Then what happens is that 1, 1, 2, minus 1.5 or 0.5, which is positive. So this is 1, minus 2, minus 2, right? So 1, 1, minus 2 equals 0. And then a minus 1/3, so becomes 0, becomes basically negative. Then output is actually 0, 0. So both 1, 1, and then 0, 0 mapped to output 0. And 1, 0, 0, 1, you can check it. It actually produces the positive value here, and then actually output is 1. So this guy is to basically, the role of this guy is to detect whether both are 1, 1, or not, then providing some necessary adjustment over here. So it's neat, if we include this guy, that is actually to handle this kind of type of program. So if you just start with this nonlinear function, and then assign these weights, that's not so much interesting. However, if you start with the blind, no weights are assigned originally. But through training, if this neural net create the weights something similar to this, and thereby solve this exclusive OR classification problem, that's neat. Because the neural net is not just mapping the input to output directly with just a linear combination, but it is to create some internal representation of the inputs coming to this one. It is to create another internal variables. With that, it is to make the right map. So this is actually an interesting part. It's called the hidden unit. Not directly visible from outside, but it's something internal in here. Okay. So inspired by this, people look at the multi-layer neural net, and then this one may be more powerful tools to deal with some nonlinear problem. The above example of exclusive OR manifested the need for hidden units for solving a classification problem that is not linearly separable, right? The hidden units generate an internal representation of the input pattern, providing the output unit with the critical information key to the correct classification. Yeah, the generalizing this hidden units role, the architecture of a multi-layer neural net was developed. So it looks like this. It has multiple layers before reaching the output layer, layer M. And layers are numbered from 0 to a final layer, capital M. And the layer 0 is basically input units, and then input units is simply distributing the incoming signals to all the corresponding the next to the layer of units. And then signals is propagated from one unit to one layer to the other, and then computation proceed in this directions to arrive at the final outputs. And the final outputs are compared to a correct one, and then we make the correction to these weights. We use the following notation. The WJI is the weight associated with the layer and unit j, where it actually, connection is being made from unit I to unit j, and then we put the two subscript here, wj, it's actually the unit number going into this. J is the unit of this guy, and I is coming from unit I. Okay, and then all summations weighted the sum as zj, and which is actually mapped to an output through nonlinear functions, like this. Now input is denoted xim. This is the layer m incoming signal from unit I. We do not specify j in here because this output is going to other units too, right? So the same signal, no need to show where it is going. But I know that this variables indicate where it comes from. That's most important. Now output is from this unit j is denoted to yj layer m, which is connected to the next layer's unit somewhere here. But that's actually used as input, and then remember that the unit subscript here is to indicate from which unit it is coming from, right? So we put the same j over here. So yjm equal exactly the same one, xjm plus 1. Okay. So this is the notation we use. Please get familiarized with it. A unit number is basically a number from 1 to m, all the way from input layers, and then going to the output one. Well, sometimes we skip some of the connections, and that's basically an architecture problem. In the neural machine learning literatures, and these units are sometimes called node. And then these weights are node weights. Okay, so multi-neural net for the path computations, and so two elements, simply, weighted the sum of the all incoming signals, and then mapped to the output through this nonlinear output function. And we will discuss the choice of output functions, but I know for the time being today, we call this kind of we use this kind of output function. It's called the sigmoid function. It's a more generic name is output function or activation function. Okay, one important theoretical underpinning is that a three-layer neural network with the sigmoid output function like this satisfy the function approximation theorem. Remember that the last Monday we discussed the radio-based functions, right? Radio-based functions and many other basis functions collectively approximate broad class of nonlinear functions, and then accuracy is important. So you provide any small positive number epsilon, but there exists a finite number of basis functions, such as this neural units that can approximate the given nonlinear functions, whereas the maximum error is bounded by the epsilon you provided originally, no matter how small you specify the epsilon. But there exists a finite number of units. So that's actually one very important mathematical theory to support these efforts. That was George Sebenko back in 1989. He called it the universal approximator. And actually, this condition has been extended in many directions. So much broader class of output function, not necessarily sigmoid functions, but other functions can do this. Yeah. So with that, now this is great. So it is a universal, function, so we can approximate the broad class of nonlinear functions. But the one question is training, and at the end, the output is compared to the correct outputs from the training data, right? And based on this, weights must be modified. But I know this final layers of units, very simple. We just have a direct comparison between these two and then make some corrections, and as we discussed before, the delta rule. But look at the units over here. Okay, the output of this one is actually propagating through this network, and then at the distal point you get the correct signals, right? So situations are very different, between this final layer units versus this deep back to close to the input layers, because the error signals is by far from this point. So how you can actually get the correct correction way to change signals, even though the correct output is presented far from this point. And then that is actually the one open questions for the multi-layer neural network. But this problem has been solved very neatly. It's called the error backpropagation algorithms. So before formulating the error backpropagation algorithms in a more general form, let's look at the simple example. This example is just good enough to understand this principle. So let's look at this. So we have only 5 units, including the input unit, and units are numbered from unit 1 to unit 5, and we have basically 3 layers over here. Okay, and then the weights and input labels are all defined in the same way as before. So just to remind you that the X3 is basically Y3 coming out of this, but this is basically, this output is also the input. So I did not use Y in here, but I know this guy is Y3, the same one as X3. Okay, so what we like to do is actually develop the weight change, weight correction algorithms. So before that, let's look at the forward pass in a computation. So given the input, it is multiplied by W21, create the Z2. Z2 is mapped to output through this nonlinear function G2. And then actually, this X2 multiplied W32, creating Z3, and output to X3. The same root over here, and then here Z5 is actually sum of these two roots, X3 W53 and X4 W54. Altogether Z5 is now mapped to the output through nonlinear function G5. So that's Y hat, which is compared to correct output Y. Okay, and we evaluate the squared error like this. Sometimes this one is called the loss function, as I said before. Okay, so gradient descent, basically weight Wji is to be corrected in proportion to the gradient descent, gradient of that loss function E with respect to that weight to be changed, the Wji. And with the learning rate and law in the opposite direction, because this is a gradient descent. Okay, now let's look at the W53. W53 is basically involved in this way. So X hat is basically output here, coming from this function G5 evaluated at the Z5, right? And then this Z5 comes from the 2 units, and actually X3 and X4 involved. So first, let's actually compute the W53, this guy, W53. This error, first differentiated with respect to, okay. So this guy is actually now, 5.3. So this is 5.3. So we differentiate. We take the partial derivatives of E with respect to W53, right? And then let's apply the chain rule. First, E is a function of Y hat. The Y hat contains in W53. So let's look at this guy. Partial E or partial y5 basically, y hat, y, they are basically the same. And the y5 is basically a function of, the z5 through this nonlinear function. So dy5 dz5. And then this z5, and as shown here, z5 contains the w, 5, 3. So we differentiate it with respect to w, 5, 3. So first one, this one is basically, from, 2 comes out and it cancels out. And so low y hat to minus y, right? And this guy is basically, through this nonlinear function, differentiated this guy with respect to z5. So we write z5 prime evaluated at the z5. And then that's actually this term. And finally, z5 differentiated with w5, 3, leaving x3. So that's why we have x3 over here. Okay, just we applied the chain rule. Now, for the following stage of computation, we replace this part. This part basically, this part, partial E or partial dz5, this term, these two terms, with the minus sign, we replace this as minus delta 5 and partial E or partial z5, combining these two. Okay, so please, memorize that, delta 5 equal minus partial E or partial z something as indicated here. Now let's move on to W32 over here. Okay, this weight coming through this channels. Again, I know this must be changed to W32 must be proportional to gradient of W, error E, partial derivatives with respect to W32, right? We again use the chain rule, okay? So, I just wrote all the relevant equations here, okay? Again, Z5 comes from here, it's given by this, and then X3 is actually coming from the nonlinear functions, and the Z3 is basically, this is the X2. X2 is, multiplied by W32, arriving at the Z3. Okay, so, let's start the chain rule, for this minus rho. First, E differentiated with respect to y5, and then y5 with respect to z5, and the z5 with respect to this end, x3, not this end, because we want to reach this point, x3, and x3 is basically, a function of z3, so x3, z3, and then finally z3 with respect to w32. So this is a chain rule, okay? Now, first, this guy, maybe we can start with this. Z3, W32, it's easy. Remember that equation, differentiated this with respect to W32, leaving only X2. So that's an X2, right? And, X3, Z3, X3, but basically this output X3 equal G3, Z3. So differentiated this. And so, that's G3 prime evaluated at the Z3, right? And then likewise, we know W dy5, dz5 is basically, this function, W, 5, 3 is actually coming out of it, from here, and then this term is interesting. So if you combine these two, we remember this, right? Partial E over partial Z. What is that? Partial E over partial Z5. This one was actually defined to be minus delta 5 in the previous slides, right? Remember that? I'm talking about this guy, exactly. So, here we see the similar things, but this one expanded to partial E of partial Y5, but Y5 to Z5. That's exactly these two terms, these two. These two can be, with minus sign, replaced by delta 5. So when running rate low, Z5, and then lengthy expressions, this guy coming in here, okay? Now for the next stage of computation, we replace this product, Z5 and delta 5, W5, 3, G prime 3, Z3, replaced by delta 3. We can do the same for this W42 as shown here. It is like the rho times the delta 4 times X2. Okay, so now the final stage, we like to actually obtain this weight, deepest weight from here, W21. We again apply the chain rule. However, be careful. You see that change to W21 influences one through this channel, the other is through this channels, right? So we have to keep track of two pathways to figure out what is actually the effect of partial E of partial W21. Okay, so first partial E of partial Z5 is the first stage, that is minus delta partial E partial delta, replaced by the delta 5, right? So that's the first thing. And then now Z5, we arrive at the Z5. Z5, one pass is through this guy, right? Z5 X3, and then X3 versus X2. Before that, we had to go through a Z3, but I just skipped that one, partial X3 or partial X2 through Z3. And then X2, W21. That's the partial derivatives, reflecting this pathway. Change also here is to influence this output through this channel. So Z5 X4, and then X4 X2, and then X2 W21. W2 X2 W21 is involved in both terms. So let's actually factor out this one over here. And then let's actually examine the other terms. So first, as I said, the partial E or partial Z5 with the minus sign, that's actually delta 5 that has been defined previously, right? So running rate low and then the delta 5. Let's examine this. This is to reflect this. Z5 X3 through this term, right? So it is actually going through W5 3, and then this guy X3 X2, G3 prime is involved, and then finally X3 X2, including G3 differentiated with respect to X2, that's actually W32, right? So that W32 comes out in here. So please actually follow this, as stated here, although I skipped some part, but you can find, and this one is the right answer. So please refer to these equations, and this just nothing but, the basic computation and functional relationship among them, okay? So it's actually consists of learning rate, and these two summations, and then W5 is something W32, and then delta 5 is something like 3, and then actually X2 W21, X2 W21. Basically these two are both X2, right? Output, right? What is involved is actually G2 prime, and then the Z2 differentiated with respect to W21, leaving only X1. So G2 prime and then X1 is to represent this term. Now representing this, let's use yet another replacement, because this actually product, delta 5, W53, G3 prime, we have seen this somewhere. That's actually previous slide over here. Delta 5, W53, G3 prime. Okay, that is exactly this guy. So we have already computed that's delta 3. And this terms too, delta 4, we have already computed in here. So no need to recompute many times the same things. So if we use this delta 3 and delta 4, we can actually simplify the computation in this way. Okay, so if you compute this in a particular sequence, and then keep the some of the intermediate results like a delta 2, 3, 4, 5, we can actually simplify and reduce the number of multiplication needed. So here's the actually summary what we have done so far. So we started with the final layer, W53, W54 computed. And in that delta 5 plays a key role. And once we know delta 5, 5-3 change is actually in proportion to running rate low and the delta 5, and then input x3. In this case, the W54 is actually use the same delta 5, but x4 must be multiplied through this channel, right? And the next delta 4 associated with the units over here, it's basically computed based on the delta 5 multiplied by W54, through this, weight, and then G4, prime must be, multiplied. Same thing delta 3, and then using these two results, we can actually compute the delta 2, through this expression. So it must be computed in this order, and then weight needs to be changed in this way. So this is what we learned from this simple, example. But the same thing applies to, arbitrary, and multi-layered neural network having many, hidden layers. The computation must be propagated from the final stage, final layer to previous layers, getting closer to the input layer, right? So for final layers, we have this direct comparison over here, and then we can actually compute the prediction error times this guy is the delta, and then actually way to change associated with it is multiplied with the incoming signals, let's say xi m, multiplied by this delta, and then that's a way to change we need to do. Okay, so all the weights w delta w ji change to that, and the layer m, which is a capital M, the final layer, is to be changed in this way. Okay, so we finish the final layer first, then actually going to hidden units, and then now the computation we found is something like this, right? Let's actually look at the delta for this actually unit j, that the delta j and hidden layer m is basically collecting the all the actually connections. This guy is to distribute. So one is actually through these channels with the weight wkj. Say suppose this one is unit k, and then unit j provide the output to this. Then we pick this weight wkj and layer m plus 1, and then actually for that one, we need to multiply its own j's output function, the derivatives, and this guy is to be corrected with this errors. So we have to know delta values of the previous actually layer m plus first units, all of them, and then take the weighted the sum of these deltas, as shown here. That's what I shown by this sigma, and then multiply by this is to create the delta for this unit j. So if you see this, taking the weighted sum, it's very similar to the forward path computation, isn't it? But I know the summation is not actually directly evaluated to create the output. Instead, it's multiplied by the derivatives of this output function. So that's slightly different. but it's a very similar to forward pass computation. So I just coined this notation and having some kind of strange notations of this round summation is coming back from the next layer back to this layer with this weight and collecting the delta information from this to compute this one. This one is layer by layer. We can actually proceed from the final layer to the first layer backward in this way. So we basically pass on the key error delta from the back to the front. So that is called the error backpropagation algorithms. Okay. So error backpropagation algorithms has a beautiful structure. The forward pass moving from input to output, you have to keep the computational results, and to some extent, and all the X values must be stored. And then after reaching the final layer, we get the comparison with the correct one, and final layer's error starts over here, and the delta value is actually passed on, propagate backward, to determine all the delta values of individual units. And once you determine the delta, then actually back to this weight need to be changed by multiplying this input xj. So that's the change that needs to be made. Excuse me, this guy, the delta j times xim for weight change wji, okay, with running rate law. Yeah, this error backpropagation algorithm was developed by basically Worbers. Yeah, 1974, but his first paper was ignored. No one responds to that. Almost 10 years later, Rammelhart, Hinton, and Williams, they published a very visible paper. And then society recognized, yeah, someone did it before. Yeah, Worbers, basically did this work, that's a story. Okay, any questions up to this point? Sorry, I just speak very quickly, but I think that some of you know something about this story. Let me take one example. Yeah, Charles, you raise a very good questions. And actually, I did not talk about something more advanced versions, more complex functions, and it's more involved, much more involved. So conditions are not that simple. I just want to show this, and because the final result is very transparent and easy to understand. But I know we need some kind of mathematical foundations. Why this kind of stochastic method really works, and then guaranteed to converge for some idealized case. In fact, the real problem is much more complex, and sometimes it converges, sometimes doesn't. Right. So that's a major actually open question to neural nets. This is just a very much theoretical and symbolic, in one sense, is not practically useful. But I know just a peace of mind, things we're doing is actually probably correct. That's all I can say for this. Okay. Any other questions up to this point?
Thank you.
Yeah. Okay. So we have many, so this is the basic things, but I know there are so many tips and so many clever ideas to make this one useful. And so let me just move on to this, and training of a multi-layer neural net with the error backpropagation. I have to talk about the output functions, sigmoid output functions and its properties, smoothing of convergence process, local minima issues, and a mini batch technique, and hyperparameters. And first of all, sigmoid output functions is actually being used extensively before deep neural net comes out. Output function GZ, it just shows some of the flavor of discrete 1, 0, or 1, type of logical functions. But instead, we like to have a kind of smooth transition from 0 to 1. So we consider that this function, it's called the sigmoid function. It is nonlinear, but differentiable. Okay, let's differentiate this. Can you differentiate this with respect to z? What happens? So if again, first if you extend z to infinite, this one and it becomes 0. So 1 over 1 is 1, right? Going to 0, 1, right? If this one goes to minus infinity, then this one shoots up. So 1 over infinite. So basically it's going to 0. So it actually goes from 0 to 1, and then smooth transition. In the middle, it's basically 0.5, right? So if z equals 0, it's 1 over 2, that's 0.5. Okay, so that's this function. So let's take the derivatives with respect to z. So 1 plus e minus z, power minus 1. So minus 1 comes out, and then this becomes minus 2. So that's actually in here, and then differentiate the e minus z with the z minus ez. The minus cancels, so this is the answer, right? This is interesting, because if you factor out the 1 over e, 1 over 1 plus e minus z, the remaining part can be written in this way. So, if this one moves up, this one is, nothing but the e minus z over 1 plus e z minus 1, right? So that's actually, same one as this. So this can be, expanded in this way. And if you see this, each of this is actually function g, right? So this can be written as, function itself, g, 1 minus g, okay? And this one is basically a parabolic function. So it takes the peak value over here and then 0 and 0 when the g equals 0 or g equals 1. Now, in this plot, I'm plotting g prime against g, not the z, okay? Z is actually, original independent variables. But now, let's, plot it, g prime against g. Okay, here we have, interesting properties we can find. So when we look at the weight change, it is proportional to the delta, and the delta includes g prime. So weight change is basically proportional to the derivatives of the output function g prime, right? So if g prime is small, the weight change is small. If g prime is big, the weight change is big, right? So let's look at this situation here and here. Weight change is to be very small because the g prime is 0 and 0 over here, right? In these ranges, actually g equals 0 and g equals 1 represent the, something like, a z value is very large, or, almost the plus, look at this, z, right? G equal 1 means actually z is almost infinite, and then, minus g equal minus equal basic, the 0 is actually z is, very, and minus infinite, right? So here, that is a case here and here, right? If that's a case, weight change is very, very small, okay? So what this means is that once the unit j has committed to take an output value of either 0 or 1, the weight wji will not, change very much, right? On the other hand, if the g takes the value of 0.5, that's a maximum. Yeah, in this case, 0.5 is just the middle point, z equals 0, right? Z equals 0. So z equals 0, we make a most actually change to the weight, just like a flip state, like Ohio, Georgia now the flip state, and Arizona. If you look at those states, the voters have not made any commitment yet. Sometimes yes, sometimes no, sometimes red, sometimes blue, right? These actually flip states are actually to receive the highest change to the weight. Okay. On the other hand, this solid blue or solid red state, no change. So yeah, no campaigns are happening over here, but this is a place the campaigns are more happening over here, right? So error backpropagation algorithms forces the unit to reach some significant, react significantly to that input. Okay. So once it's settled down to either this side, no more change, right? So in a sense, actually, this property contributes to the stabilization of the learning process. So this is the one interesting properties. Although going to deep learning, this is not a good, property. So we, consider the different output function. But I know for most of the stuff, this is okay. Second point, the smoothing of a convergence process. A typical failure scenario of a neural network, is basically zigzag kind of stuff. And this happens for class of, kind of a failure scenario is that when we look at the, plot of cost function Jn against the weight W1, W2, there are many, many weights over here, right? If you cut it at a certain levels, we can actually plot it in this kind of iso Jn line. So this is the minimum point. Okay, we want to reach this point, but let's think about the situation. We call that steep ravine. So this side is very actually steep wall. This side. Okay, and like a Grand Canyon. So if you sit in one side of wall of the Grand Canyon, your gradient actually point in this direction. And, this is kind of a very narrow, channel. And then even though you put the some decent learning rate, you push to this point. And here you, again, it's actually bounce back to this point. And then sometimes even farther and actually going back and forth. So it is to diverge. So if you slow down the process and then tuning in a very small learning rate, yeah, maybe that's okay, won't actually diverge, but I know the convergence process is extremely slow, painfully slow. You have to wait for a long time and it takes a long time to reach this point. So this is something that we don't want to have. So what is a remedy for this? It's called the momentum term. And what you do is, this is the previous step. You found that this one is actually a weight change you made. And then next step, getting the different actually directions to change the weight. This is the weight space, going this way. But I know don't execute this change. Sometimes this one is the zigzag. Instead, keep some of this previous one as a momentum terms, with some multiplication alpha is smaller than 1, and then take the this one to this extent and add it to this. So take this, execute this way to change or the next time. So this one is more actually smoother transition than the previous one. So this is called the momentum, the technique, and we tune this in parameter alpha, proportionally constant. Local minima is a big issues, and you want to actually, minimize the your cost, loss function. But this is the nonlinear optimizations, and so it is likely you get stuck at the local minimum, like this point, right? So how to get rid of this local minimum? This is just, kind of a, tip. One very well-known tip is to actually train a neural network multiple times, starting with the diverse initial conditions. So that makes sense, right? Well, if you happen to start with the this initial conditions, you basically arrive at this point. If you start with this one, converge to this. You are lucky if you pick the this initial condition, you arrive at this point, which may be actually better than this, right? So the idea is that, initial condition, where to start, you randomize this and then take the many, cycles of training, and then each arrive at some local minimum. And if you're lucky, the global minimum will be involved. And then look at the all results and then pick the best one in terms of the squared error or loss functions. And then that's actually techniques that are being used. Mini batch training. So this is yet another tip that is being used. You remember that the classical Wheeler-Hoff stochastic gradient descent method makes corrections to node weights for every single, the data point presented to the neural net, right? And here's actually pros and cons. I just emphasize the pros side. Not much memory space is required to implement this, because every single presentation, you make a quick change. You can forget about the previous results, right? And also, this method is interesting because of the large kind of erratic motions of going right, going left, random work. So sometimes it works very, very effectively for getting rid of local minima. So this local minimum, if the weight change and you make is almost random, actually perturbing this a lot, you may actually go over this a peak point to comes to a good region where you will actually reach this global minimum. So perturbing this is not a bad idea. So if we can take advantage of that, there's actually small just a presentation by presentation change is, and that makes sense, right? But cons obviously is to induces more noise in error calculations, in particular when it's getting closer to the final local minimum or global minimum. It's too perturbing. So it is very difficult to tune the learning rate, even though you applied some learning rate change rule, but it's actually not easy jobs, and because of the large fluctuations. So taking that the middle ground is actually technique called mini batch training. So alternative is the mini batch training, where a small set of data points are presented and the gradient is computed as the average of the gradient obtained from the small set of data points. So if we have many data points over here, right? So in this case, mini batch is the size of 8. So you present 8 input examples, and then calculate the output and evaluate the error for all the 8 cases, and then actually integrate these to make one change to weight over here. And then we repeat this many times. In practice, kind of a rule of thumb is a mini batch size of 32 is commonly used. Okay. So, in addition to the weights you basically change, optimize through training, you need to provide a bunch of parameters that must be specified before you proceed for training, right? So these parameters actually net training depends on the structure and the parameters that must be specified prior to training. And this is the list of parameters you need to pick: the learning rate and the number of hidden layers, how many hidden layers, and how many units in each layer. And the mini batch size, do you stay with the 8 or 32 or 64? And the epoch size and how many, capital N, right? And then choice of output functions. These are stuff you need to pick. And these are kind of, the techniques that you have to consider. Now, let me just, I don't want to execute, overrun, but let me just show you the, context-oriented project number 4 was released today. And actually, it's due after Thanksgiving, November 30th. So you have 2 weeks. Okay. And then you will discuss this Friday. The first problem is just a warming up problem, and that's actually simple. Part two is actually robotics problem, and then what you need to do is to actually control this robot. Just looking at the algebraic nonlinear functions, it's called the kinematic equations. So this robot joint angle Q1 and the Q2, and then that's located in the endpoint, describe the X1 and X2. So what you want to do is basically this robot, having this kind of an input-output relationship, Q1, Q2 joint angles, and X1, X2 is actually coordinates of the endpoint. Now, to move the robot to the desired X1, X2 coordinates of the endpoint, you need to solve this, inverse kinematics problem. It's actually a nonlinear simultaneous equation. So sometimes it's very difficult to, solve the inverse kinematic problem. But I know we can solve this inverse kinematic problem by using a neural net. So what you see here is that here's actually a simple neural net connected to a robot kinematic model, basically this model. Okay, so this one is to compute the X1, X2 based on the from the joint displacement. So this is for the pass, simple evaluation of these equations. Okay. And what you need to do is to present the desired position xd1, x desired 2, and then let the neural net compute the q1, q2 joint angles, which is actually converted to endpoint coordinates. And then that's actually compared to your desired output. Error may result, right? And then based on this error, we like to tune these weights so that this part is to represent the inverse function to this, right? Inverse function. So output is not actually compared to the correct joint angles, but instead is actually compared to this one. But I know when you backpropagate this error, you can just use this equation to make a corrections, right? So in the same way, you can just compute the error, and then actually backpropagate this to way to change over here. Okay, that's the first question. And then the second question is more interesting, and then third question is even more interesting. Well, we look at the situation that instead of using this, this nonlinear algebraic functions, but we replace this one by yet another neural nets. That's actually this guy, neural nets. Okay, first you train the forward kinematic function relationship for input-output relationship. You can train this neural nets, right? And then after train this, you can train this neural net one. This is the inverse kinematics part, and combine these two neural nets together. And the error is here, backpropagate through neural net 2, and then arrive at the neural net 1. And here's some signals, R1, R2, and the question is, what is the physical sense of R1, R2? Can we really train this inverse part based on this? Yeah, the answer is yes. But in solving this, I want you to do this. In training a multi-layer neural network, we need to provide the hyperparameters values, right? Including learning rate, the number of hidden layers, the number of units in each layer, the mini batch in the size. Please actually try out these parameters and see what happens. What the sort of network structure best works for you. And this actually choice of hyperparameters is one important job. I want you to get familiarized with it. And then, question 3 is more interesting, but I hope you can read that and then discuss it in this Friday. Okay, so that's all about it. And any questions? So I think the neural net is not complicated. It's not difficult math at all, but there are lots of actually, kind of tips. How to say, many techniques need to be, tried. But if you are able to do that, this one is absolutely useful tool. So for your techniques. Okay, any questions or any concerns or anything? It's very straightforward, right? In a sense, if you go a little bit deeper into that, it's a whole very complex, and the whole nonlinearity is very complex. But just using this, it's not the difficult job. Yeah, yeah. I think many of you already use this in some extent. But I know this, context-oriented program is to enhance your understanding of the materials. And then I hope you can enjoy solving this. Okay, with that, let's conclude today's lecture. Okay, we'll see you this month, Wednesday. Take care. Bye.
All right, thank you.
Bye.